let's go over some applications of these triple integrals. Most of this is going to be very similar to the stuff that we did with double integrals. In fact, there's not really anything that we're going to be covering right now that's not going to be essentially just lifted straight from what we did with the double integrals. So first things first, recall with double integrals, when we took the double integral over some region D of the function 1, all that we end up getting was the area of that region D. So if we have some D here, we can express the area of that D as a double integral of 1 over that region. The same thing is going to be true for triple integrals. So we have our some region E in three-dimensional space. The triple integral over that E of the function 1, this time it's instead of dA it's dV, is the volume of that region. Now maybe that doesn't really seem too helpful, but it can be very helpful if you already have something that's set up to already be 1, if you can figure out what the volume is from geometry, you can actually make use of this. Or we can actually use this as a way to compute volumes. So the way we were computing volumes before, we were actually thinking of the type 1 regions where we have some top surface and some bottom surface. So if E is some region where x and y vary over some region in the plane D, and then the z values are bounded between two functions of x and y, then the way we set up our triple integral of 1 specifically, we set this up as a double integral over D of the integral of gxy to hxy of 1 dz dA. But when we integrate 1, we just get z, which means that we end up subtracting h minus g. So it's the double integral over d of h of xy minus g of xy, which is pretty much exactly the way we were talking about volumes using double integrals. But what this allows us to do is use any of our orderings of x, y, and z. This is specifically when we're doing a type 1. We could do type 2 or type 3 regions in three-dimensional space and compute the volume this way. So let's look at an example of that. We're going to take a given solid. Specifically here, they're giving us two surfaces, y equals x squared plus z squared, and y equals 8 minus x squared minus z squared. We want to look at the solid that's inside of both of those paraboloids, and we want to find the volume of that. Of course, we might as well go ahead and plot that region. So y equals x squared plus z squared. Y equals 8 minus x squared minus z squared. We have two paraboloids. And we specifically want to find the volume that's inside of both of them. So this kind of, I don't know, almost football-shaped region in here. If we wanted to set this up how we were doing that with double integrals, using our techniques from before, we would have to we'd have to actually look at this region in the xy plane. This is the region between two parabolas. That would be the region that we'd have to integrate over. And then we'd actually have different upper and lower surfaces above, depending on whether or not our y values were below 4 or above 4, which essentially means we'd have to split this up into multiple integrals in order to actually even do it. if we were to do that, maybe we'd have something like the volume is equal to the integral from -2 to 2 of the integral from, let's say, x squared to 4. Our upper and lower surfaces are actually fairly complicated looking when we're actually doing them as z equals something. We'd have to solve these equations for z. This first one, we'd be looking at this first paraboloid for this setup for this first integral. There, z is equal to this, let's say, y minus x squared square rooted, but then we have to have the positive part of that square root for the top one and the negative part of that square root for the bottom one, which essentially means we have 2 times the square root of y minus x squared, and this would be dy dx. But then we have the other part. This would be still be from -2 to 2, but this time instead of going from our first parabola up to 4, we go from 4 up to our second parabola of 8 minus x squared. This time now we're using this paraboloid. We do the same kind of thing. We have 2 times the square root of 8 minus x squared minus y dy dx. Now, this is something we could probably evaluate. We'd have to know how to deal with the square root of something with x squared in it, something like that. But this is already kind of messy, and we probably wouldn't be able to avoid having to use some sort of trig substitution in the long run. Specifically, when we have, say, square root of 1 minus x squared, the way we would do that is by substituting x equals sine, or sine of theta, or something like that. So this maybe wouldn't be the easiest way to do this problem. Instead, let's think of this as a triple integral of 1, where we treat this thing as a type 3 region. Type 3 specifically because this is bounded by 2 surfaces, both of them y equals a function of x and z, and that's what a type 3 region is. So as a type 3 region, our volume, we'll just say it's the integral over d. We'll figure out what our region of integration is in a moment. But we are basically integrating from x squared plus z squared up to 8 minus x squared minus z squared of the just 1 dy dA. In other words, because when we integrate 1 with respect to y, we just get y, which means we end up getting to subtract these two. So we have 8 minus x squared minus z squared minus x squared plus z squared. Or in other words, we just have 8 minus 2x squared minus 2z squared. Alright, now we need to figure out what d we're actually looking at. So remember here, d is going to be a region in the xz plane. If we look at our setup here, so we essentially want to ignore the y. Think about what is the region that we're integrating over. Well, it's actually going to be this circle that we can see here, or really should say the disk. And this goes out to a radius of 2. So this is 2 here on the x-axis, it's 2 on the z-axis, -2, -2. So we're integrating over a disk. Since we're integrating over a disk, and you can already kind of see here that we have an x squared plus z squared in our integrand, this actually is really set up nicely for polar coordinates. Of course, in this case, again, we're dealing with coordinates in x and z instead of x and y. So we're just going to say that z is going to play the role of y. So in fact, we don't even have to set up the equations this time, because with our notation here, with our x squared plus z squared, we'll just use that x squared plus z squared equals r squared. Of course, we're going around the entire circle, so we're going from 0 to pi for theta. R is going to go from 0 to 2, because there we have a radius of 2. Our integrand here is 8 minus 2r squared. We have an extra r from polar coordinates, dr d theta. Of course, there's no thetas in here at all, so actually the integral over theta just becomes a 2 pi on the outside. Looking at the integral from 0 to 2 of 8r minus, 2r cubed. Integral of 8r minus 2r cubed is going to be a 4r squared minus 1/2 r to the 4th, still from 0 to 2. When we plug in 2, we have 4 times 4 is going to be 16, minus half of 16 is going to be 8. So that becomes an 8 times 2 pi, or 16 pi. So actually, not too bad. Definitely a lot nicer than what we had originally. So this gives us a way to compute volumes of these solid objects that might otherwise be a little bit more complicated to do. Now we could also even view these solids as not having a constant density. We can look at some sort of density function. Even write this in here, density function, rho of x, y, z, where the density at any given point x, y, z is given by this function. If we have something like that, we could consider the mass of the solid. And we do that the same way we did back with double integrals. There we are looking at the mass of just a flat plate, because we really wanted to think of a mass of a two-dimensional object, but we wanted to think, since we want to think of mass as a three-dimensional idea, we need to actually think about it as having a little bit of a thickness. Here, since we are going to be dealing with regions in three-dimensional space, this might make even more sense. So if we have something here with some density function over this thing, we can actually compute the mass of that solid by use of triple integrals. So here the mass is just the triple integral of the density function over that entire region. We can also compute the center of mass. Basically, we're going to be computing the balancing point of the solid, where essentially we could treat the entire mass of the solid as kind of being at that point. We have to compute first the moments around the coordinate planes. So we have these various formulas. So the moment around the YZ plane, we're essentially taking the distance of a point from the x. So basically, the distance from the YZ plane is x. So we're going to take that x times essentially the density function is playing the role of what is the mass at that distance from the YZ plane. And we do that for, well, we integrate that over the entire thing. So each point is essentially going to have some distance from the YZ plane, and it essentially plays the role of some torque around that plane in a sense. We do that for each of the 3 different planes, each of the 3 different coordinate planes, and we get our center of mass. So be x bar, y bar, z bar. We essentially just take these moments and we divide by the total mass. So for the x bar, we actually take the moment around the YZ plane, MYZ, divided by little m. We have, for y, we have MXZ, divided by little m, and then MXY, divided by little m. Notice that when you actually compute these things, the integral that corresponds to a given coordinate, so say for x coordinate here, the integral there is the one that has the x in it. Same thing for y. The integral that we're actually dealing with on top has the y in it. And then for z, we have the z in it. So if you don't remember exactly what the notation for the moments, how that goes, just remember that we're essentially taking the integral of, for each of the coordinates, we're taking the integral with that coordinate times our density function divided by the integral without any of the coordinates in it. So as an example, we're going to work out problem 39. So we have some solid E that we want to find the mass and the center of mass of this solid. Now in this particular case, our density is actually constant. That actually will save us some work overall. Well, I guess maybe not necessarily save us some work, but at least it'll make the integrands very nice. And it'll allow us to actually view this as just being the center of mass of the region that we look at. We don't have to worry about different densities. It'll make it look a little bit. It'll definitely make what we end up getting look like the center of the solid that we draw. Now, of course, we're going to go ahead and actually plot this before we even get started. So E here lies above the xy plane and below the paraboloid z equals 1 minus x squared minus y squared. So we go ahead and plot that. So we have this paraboloid here. We're going to go ahead and plot our z equals 0 as our xy plane. We're only looking at the part that's above that plane. So we have this solid up here. We want to know what is the center of mass of that solid. Now you might be able to make a few guesses about where that might belong, but we're actually going to go ahead and just find that using the integrals to just make sure it does agree with what we might guess it to be. But the first thing we need to do is find out what the mass is. What is the mass of this solid? Well, it's going to be the triple integral over that solid of our density function, which is just a 3. Now, of course, since our density is constant, we could just pull the 3 out. We're really just kind of looking at 3 times the volume of E, but we still need to be able to find the volume of E. I'm going to go ahead and actually set it up that way. So we're essentially, let me put it this way. Because we are essentially integrating this over a disk, we can definitely view this as we have a top surface of 1 minus x squared minus y squared, and then a bottom surface of 0. Then we're going to be looking at type 1 region here. Our region in the plane is definitely the circle of radius 1. We'll just go ahead and use polar coordinates for a lot of these calculations. In fact, probably all of these calculations. Of course, going around the entire disk of radius 1, theta is going to go from 0 to 2 pi. R is going to go from 0 to 1. Our integrand, remember, well, I guess we can even go ahead and set this up. So our z is going to go from 0 to 1 minus r squared, because the x squared plus y squared is r squared. Then we have dz. We need the r for polar coordinates. Then we're going to have dr d theta. We can view this as kind of, we have this integral before we do the integration for polar coordinates. I guess right away, we don't have any thetas inside here at all. So actually, I'm going to turn the integral from 0 to 2 pi into 2 pi on the outside. That's going to combine with the 3 that we already have there to be a 6 pi. This integral here just becomes a 1 minus r squared. So 1 minus r squared times r is going to be r minus r cubed. So we have 6 pi times the integral of r minus r cubed is 1/2 r squared minus 1/4 r to the 4th. So Always want to make sure these are brackets to basically signal that we haven't put in our limits yet. Putting in 0 obviously just gives 0 on the inside. Putting in 1 gives us a 1/2 minus a 1/4. 1/2 minus 1/4 is a quarter. A quarter times 6 pi is going to be 3 pi over 2. That is the mass of this object. Now, the volume here is actually pi over 2. But since we had a density of 3, it's the mass of it is 3 times that. We'll go ahead and compute our moments. So remember, myz is a triple integral of x times our density. Our density here again being 3, so really we're just integrating 3x. I'm going to go ahead and pull out that 3, and we'll set up our integral just the same way. We're going to be going from 0 to 2 pi, 0 to 1. Our z values are going to go from 0 to 1 minus r squared. We're going to have an x in here, but remember, x is actually our cosine theta. And don't forget your r drd theta. Really, we could actually even move the r inside. So we're really going to be doing r squared cosine theta. Of course, since there's no z's in here, we're really just get to end up multiplying by 1 minus r squared. So we have 1 minus r squared. We have r times an r, so we have another r squared. We have a cosine of theta, drd theta. I'm going to go ahead and split this up. So we have that 3 still out there. The cosine of theta, we can just go ahead and do the integral of that out here. Then we have the integral from 0 to 1 of this stuff, which I'm going to go ahead and write as r squared minus r to the 4th. Integral of cosine is actually just sine. Integral of r squared minus r to the 4th is 1/3 r cubed minus 1/5 r to the 5th. But now something kind of interesting happens. When we plug in 2 pi and 0 into sine, both of those give us zeros. So actually, this part's 0 and none of the rest of it matters. So that's kind of interesting, but maybe not totally unexpected if you know what to look for. We'll come back to exactly how you might predict that in a moment. But let's actually go ahead and find the other moments. So here, mxz is y times our density integrated. Of course, we're going to set this up the same way. Remember, our density is 3, so I'm going to pull out that 3. Our thetas are still going from 0 to 2 pi. R's are still going from 0 to 1. Z's are still going from 0 to 1 minus r squared. This time we're integrating y, but y is r sine theta. We still have the r from our polar coordinates. I'm going to move that inside here. Integrating the z part, we have the 1 minus r squared that just gets multiplied in there. So we have a 3 times this integral. We have 1 minus r squared times 2r's times sine. We do exactly the same kind of thing that we did before, where we split this up. We have the integral from 0 to 2 pi of sine of theta times the integral from 0 to 1 of r squared minus r to the fourth. Integral of sine is negative cosine. And then we still have the 1/3 r cubed minus 1/5 r to the fifth. And then kind of similar to what happened before, but a little bit different. When we plug in 2 pi and 0 into cosine, we don't get 0 this time, but they both turn into a 1. So we have a negative 1 minus another negative 1, or negative 1 plus 1 is 0 again. This integral here is 0. That means this whole thing turns out to be 0 as well. So again, all this stuff over here with the r's really didn't matter in the long run. Again, you might have been able to predict that, and we'll explain why in a moment. But let's look at our third moment. This one is going to be the more interesting one. So again, the moment with respect to the xy plane is the one where we take z times our density. Of course, our density is just 3. We're going to set up our region the same way. We take 0 to 2 pi for theta, 0 to 1 for r, 0 to 1 minus r squared for z. But this time we have a z inside, and that's going to change that first integration. Of course, we also have the extra r from polar coordinates, but then we have dz, dr, d theta. When we integrate with respect to z, we do not just get to multiply by 1 minus r squared, because we have a 1/2 z squared inside that. I'm going to go ahead and pull out this 1/2. I'm going to pull it outside. So we have 3/2 outside. But also we can notice that we don't have any thetas on the inside. We're never going to end up with a theta on the inside. So actually we can take this integral from 0 to 2 pi and turn it into a 2 pi outside. So 3 times 2 pi times 1/2 is going to give me a 3 pi on the outside. We'll have the integral from 0 to 1 for r. But what we have inside here is 1 minus r squared squared, because we put that in for z, times the r that's already there, minus 0, obviously, dr. To actually integrate that, we're going to have to expand this out. 1 minus r squared squared is actually 1 minus 2r squared plus r to the fourth. When we multiply that by r, we have r minus 2r cubed plus r to the fifth. The integral of that is 1/2 r squared minus 1/2 r to the fourth plus 1/6 r to the sixth. But we're just plugging in 0 and 1. 0 gives us 0, obviously, so we just plug in 1 for all of the r's. And the 1/2s actually cancel each other out. So that's pretty nice. So, oops. Did not notice my click, did it? 3 pi divided by 6 is going to be pi over 2. So that moment actually is not 0. And that means that our center of mass, which I'm going to go ahead and put back up here. Our center of mass, x bar, y bar, z bar. So x bar is myz, which was 0, divided by our mass of 3 pi over 2. Y bar is mxz, which again is 0. Still over 3 pi over 2. And our last one, our z bar is mxy, which is pi over 2, still divided by a mass of 3 pi over 2. Or in other words, this is 0, 0, and this is just 1/3. So let's plot that center of mass. And maybe make this a little bit... Actually, it's kind of supposed to be pretty big. It's just really hard to see inside there, isn't it? Maybe if I make this a little bit lighter. Yeah, that's a little bit better. So our center of mass is this point A that's right here in the middle here. And don't move it. I didn't want you to move it. Now, the reason why I said that the moments around the YZ plane and the XZ plane, it wasn't really surprising that they came out to be 0, is because this is already kind of nicely symmetrical. Since we would expect that our center of mass would actually be on the z-axis, because everything should be nice and symmetric around the z-axis. And so we would expect to get zeros out from those two moments just for that reason. The moment around the xz plane is the one that's going to determine how far up or down we are, and that one might not have any idea, just based off of the picture here, where that should be. So that was the one that we'd expect to actually have to compute. The other ones, if we just make use of the symmetries of our picture here, we could have figured those out without doing the integration. But it's very important that our integration did give us the results that we expected. And obviously, if our mass was not a constant, obviously if our density was not constant, that intuition wouldn't necessarily work. We'd have to know that our density function had those same kind of symmetries in order to make use of that idea. But at the very least, when we graph this point, it definitely looks like it really should be the center of the solid. And that's the kind of idea that we're trying to capture here. So those are just some of the ideas, some of the applications that we can have of triple integrals. The book goes through a few more of them, like being able to talk about electric charge, or the joint probability density functions, where here we'd be dealing with 3 random variables that can all depend on each other. So similar things that we did with double integrals, just in a 3-dimensional context, you might say. But I'm going to go ahead and leave it off here. We've already had 3 videos on all this, so it's a fairly long section. But most of the concepts shouldn't be completely new. Just, again, 3-dimensional instead of 2-dimensional now. So I'll leave this here. In the next section actually will probably be a little short, because it's kind of covering some of the stuff we've already been working with, just actually giving it some names. So I'll leave that for next video, and I'll see you there.